So the first thing I'm going to do is sort of underline, since I can, the key information here. You set up your camera at ground level 2,000 feet from the launch pad. That's probably important. Camera's mounted to a computer-aided tracking system. That's important because that's what allows you to keep the rocket in its viewing window as it goes along. Okay, so it's sort of like a computer program is being written here. It knows how fast the rocket is going to be going. So then the computer program allows it to adjust. The rocket, when launched, ascends to space according to the position equation, S equals 50t squared. And then it says S is measured in feet and t in seconds. So now we have the units for this problem, feet and seconds. We are in feet here as well, so that's good. Find the rate of change in the angle of elevation. That's what we're looking for right there. That the video camera must utilize in order to keep the rocket in its viewing window at 10 seconds after liftoff. So 10 seconds after liftoff is going to be our specific t that we're going to be using, okay? So we have a specific t here. We have a specific distance for our camera away from the launch pad. We have an equation that we're going to be talking about. That looks like about it for the specific information. So, draw a picture. Here's my launch pad, and I am 2,000 feet away. Here's my camera. It's actually a really good 6-pixel camera. And all I did was draw a squiggle. Pretty good. I may have done this problem a couple times before. No shark face on this guy. Okay, now our rocket launches, okay? Now I'm not going to take the time to put the detail of the rocket launching in there, but basically we'll model that as being a little circle. Okay? So that's our rocket. Now we also have this line of sight from our camera up to the rocket. So right away you can see that I've drawn a right triangle. As soon as I see that I have a right triangle in this picture, I know I'm going to be using the Pythagorean theorem in some way, right? But here's the issue. It says find the rate of change in the angle of elevation. What is that? What is angle of elevation, first of all? Yeah, you're looking up, right? An angle of depression would be looking down. So we have an angle of elevation, which means I'm looking at this angle right here as my theta. Doesn't have to be theta, but we usually use theta for angles, so I'll just call it theta. Okay, does this number right here change? No. So I'm not even going to bother with defining a variable here. This is just 2,000 feet. Does this change? Yes. And we called this what letter? S. So this is S. Now, because that changes, when we write our equation to take the derivative, we have to use S. But at our particular time, do we know that distance? We could plug in 10 to find that height. Yes. Okay, good. What about this? Does this distance change? Yeah, so we're going to call that something else. And since we haven't used H, I'm just going to call that H. The lettering here is probably seeming a little bit backwards of what it should be, but it's a position function, and that's why we're calling this S, the position off the ground. Normally this would probably be called S, but that's what we're dealing with here. Okay. So the next thing we need to do probably is come up with some sort of equation that we can use. We do need that angle. Cosine or sine or tangent, right? Okay. So what? Tangent theta equals what? S over 2,000? Okay. So let me write that down. Tangent theta equals S over 2,000. We can figure out what S is at our given moment in time, right? But what we've just done is developed an equation actually very easily in terms of the two things that we don't know. Theta We know that we need a d theta over dt because we're looking for rate of change of the angle of elevation. So we have to have an equation in terms of theta. And we also need this s because that's what's changing. Okay? Now we can find this distance here, but do we need it? Not explicitly. We might need it to work with like Pythagorean theorem to find this length or something down the road, and we will, but we don't actually need it in our equation. So it seems like a Pythagorean theorem problem, and it is a Pythagorean theorem problem, but the equation we're going to use is actually this one right here, and you stumbled across it first try. Nice job. All right, so just in case we need it, let's come up with some sort of expression for h and s. So that is using the Pythagorean theorem. Well, the Pythagorean theorem says the hypotenuse squared is equal to the sum of the two sides squared, right? So the hypotenuse in this case is h for hypotenuse equals, square root, you could go s squared plus 2,000 squared. Okay? I've just saved us from having to write the second step. Okay, so now that we have that, let's figure out, we know that t is 10 seconds, let's figure out what the h is going to be and what the s is going to be so that we know all of these lengths in this triangle. Make sense? Just in case we need it. I don't know if we do or not, but maybe we do. So if I want to find this length right here, what do I need to do? No, I'm actually going to use this. The position equation, s equals 50 times 10, because we're talking about 10 seconds, and we're squaring that. So s equals 10 squared is 100, so that makes this 5,000. So at 10 seconds, the rocket is exactly 5,000 feet off the ground. So now we can find h, if we need it. That's right. Is this going to be a nice number here? All right, so let's leave that, let's let that be. We might not actually need that distance. But we are going to need this one for sure, because we know that we're going to have a theta, we're going to have an s. Okay? So, are we ready? What do we do? Take the derivative. All right, we have tangent theta on the left. We have s over 2,000 on the right. We're taking the derivative with respect to t. So, no, we can't. We have to, this is a variable. We have to take the derivative including all of our variables. Okay? Down the road, once we've done that, then yeah, if we have an s, we can substitute in that value. But we have to have the original equation and take the derivative of it before we substitute stuff in. So I need to take the derivative with respect to time of tangent theta. What do I get? Secant squared theta. So d theta dt. Right? Okay, equals? Yes. That is a 1s, so it's like 1/2000th times s. So when you take the derivative of that, the s goes away and you're left with the 1 over 2,000. Is that it? Times ds over dt. Is that it? Okay, now what are we looking for here? What's the thing we are trying to find? We're trying to find d theta over dt, the rate of change in the angle of elevation. That's what the computer needs to know to track this thing. So we are solving for this. So what should I do? So divide by secant squared theta, but what is secant squared theta? Use an identity. What do you get? No, not that identity. What is secant? 1 over cosine. So this is actually 1 over cosine squared theta. So instead of dividing by secant, let's multiply both sides by cosine squared theta. Okay? And now we have d theta over dt equals cosine squared theta over 2,000 times ds over dt. Okay, so from this point, there's an easy way to go and there's a hard way to go. You want to go the easy way, which means you need to switch the way you were thinking from earlier. The Pythagorean theorem in this case is nice if we want to find the distance from the camera to the rocket. But we don't need it. We need to come up with some sort of expression so that we don't have to work with cosine. What is cosine as in terms of SOHCAHTOA? Adjacent over hypotenuse. All right. Well, the adjacent is what? So we have 2,000 over, so let me write this. Cosine theta equals 2,000 over, what's the hypotenuse? Yeah, we got it sitting right here. It's the square root of s squared plus 2,000 squared. So if I have cosine as this, and over here I have d theta over dt equals cosine squared theta over 2,000 times ds over dt, I can take this result and substitute it in right there. And now we don't have to deal with trigonometry here. Okay? We're all down to just like letters and numbers without trig functions. So that's nice. D theta over dt equals, that is cosine theta squared. So I'm going to write 2,000 over the square root of s squared plus 2,000 squared. All of that being squared, still over 2,000 times ds over dt. The only thing here that I don't know, because I know what s is what? ds over dt. How am I going to find ds over dt? Yes. The original position function gives me my ds over dt. If I take the derivative of s, I get ds over dt equals 100t. And I took the derivative with respect to time, so there is no dt over dt here. Okay? So now instead of ds over dt, I can substitute in the 100t. And t in this case is 10. So actually I'm substituting in 1,000. And s is 5,000. So if I square, the square root's going away. So let me rewrite this one more time. D theta over dt equals, this is 2,000 squared over s squared plus 2,000 squared, all over 2,000 times 1,000. So we can substitute in the s, which is 5,000 here. And if it was me, I'd just go ahead and leave it, change it, flip it on this, and realize that the 2,000 and the square goes away. So 2,000 divided by 5,000 squared plus 2,000 squared, and then all that times 1,000. What do we get? Two over 29 is the right number, but now we need to figure out the units. Okay, it's an angle, so it's either going to be degrees or radians. We're talking about, I don't see degrees anywhere in this problem, so it must be radians, but it's a rate of change, so it's radians per second. We didn't talk about degrees anywhere. There were no angles entered in or anything like that, so it's radians. Yeah, radians are actually, you can think of them as a non-unit. It's true. Does that help? That's your answer.